Today's lesson is on our first idea of what we can do with this idea of integration. And we'll continue it into the following lesson. It should be fairly short. Excuse me, I'm a little bit sleepy, so I'll try not to make too many mistakes, but I'm pretty tired today. And so we're going to start with this little exploration. Usually would take quite a bit of time in class to work through this, but I'll do it a little bit faster since we're on a video. And so what we want to do is estimate the area A, some area A, that is enclosed by this curve, y equals x squared plus 1, also by the x-axis, the horizontal axis, and the lines x equals 1 and x equals 3. Those are vertical lines at 1 and 3. And so I'm going to come down here and kind of show you the area I'm trying to estimate between 1 and 3. X equals 1 and x equals 3. The x-axis, which is right here, and this curve here. And so I'm looking for the area of this shape right here. And so you might think, okay, maybe to estimate that area, I could actually just even find the area of one idea might be this trapezoid. Oh, if I could kind of connect this point to this point with a straight line, which I'm having trouble doing on my little writing implement. There we go. Maybe I could find that trapezoid. It'd be a slight overestimate, but I could do that. And that's often what students say. And I say, well, today we're going to do something a little bit different. We're going to estimate the area actually using some rectangles. And so what we could do is we can make rectangles under this curve, sort of like so. So we have a rectangle here, a rectangle from here to there. Oh gosh, I'm having a lot of trouble. There we go. Maybe put a point here and draw a rectangle here. And a point here and draw a rectangle here. And so I could pretty easily create 4 rectangles and find the area of these 4 rectangles. 1, 2, 3, and 4. It would be a so-so estimate. It'd be a slight underestimate. So then usually in class, what we say, okay, well, let's then do the same thing over here, but maybe make rectangles, but using kind of, we're still going from 1 to 3, but notice how on the left-hand side, I use kind of the left-hand bound, or where the left part of the rectangle intersected the curve to make my right triangle. So what if I use the right-hand side of the curve, or the right-hand side of the rectangle? So that's a rectangle, the right upper corner of the rectangle where that one intersects the curve. And so I could go like, oh, that's not very good. Let me draw this point first. There we go. There's another rectangle. Let's draw it right here. Why did I choose 4 rectangles? It was pretty arbitrary just because the grid lines were there. What would happen if I used, you may ask questions like, well, what would happen if I used more rectangles? What would happen if I used fewer rectangles? Well, if I used more rectangles, it would end up becoming a bit more precise and a bit more precise. And so here, 4 rectangles, and I could find the area of those 4 rectangles, and it would be a slight overestimate. And so what I've done is I've actually found the area of these 4 rectangles. To find this point here, we can substitute 1 into the function x squared plus 1. So 1 squared plus 1 is 2. So I can see that the height here of the first rectangle is 2. That's the point 1, 2. If I substitute 1.5 into that function up there, I get 3.25. So this is the point 1.5, comma 3.25. The next point is 2, comma, what do I have? 2, comma 5. Of course, if I substitute 2 in, 2 squared plus 1 is 5. So this is the point 2.5. And then finally, I'll find this point here, which is substitute 2.5, right? The 2.5 here into this function, 2.5 squared plus 1 is 7.25. So this is the point 2.5 comma 7.25. Why am I finding that? Well, because that's the height of each of those rectangles. So if I wanted to find this area here, I'm going to call it the lower area, or the left. Oh, I'll call it the lower area because it's going to be a slight underestimate. So I'll call it the lower area. Now I can find the area of each of these rectangles. Base times height. So base is 0.5 times the height of the first rectangle is 2, plus the next rectangle also has a base of 0.5, plus the height, which is 3.25, plus the next one, 0.5 plus the height, which is 5, plus the next one, 0.25. Sorry, 0.5 is the length of the base, and the height is 7.25. And if I add all those together, I get 8.75 square units for the area, an estimate. Clearly, yeah, that's an underestimate, 8.75 square units. If I did the same thing over here, the height of each rectangle, and so to find the height of the first rectangle, well, the height of the first rectangle is when y is 1.5, so it's 3.25. The only one that I'm missing is the height of the last rectangle, which would be 3 comma, and if I substitute it in the function, 3 squared 9 plus 1 is 10. I'm not going to do all the work to find the area of these 4 rectangles added together. I'm going to give you the answer to save some time. We're going to call that the upper area because it's a slight overestimate of the actual area. And the upper area is 12.75 square units. Well, what I know for sure is that neither of these are correct, but I know that the real area, I'm going to call A the real area. We actually called that in the problem. A is the area that I actually want. I know that that real area is somewhere between 8.75 and 12.75. I actually wrote it like this in my notes, between the lower bound and the upper bound. It's somewhere between those two. And you can read what I have written below here. The more subdivisions we make, the smaller we make the widths of our rectangles, the more rectangles we have, the more and more accurate this estimate will become. And then those two bounds on the outside will slowly get closer and closer to the actual area, the value of the area. And then what we have here finally is a little exploration. And I recommend you click that in your notes and play with it for a little bit. We could even type in the function that we just worked with, x squared plus 1. I can say I want the area, I don't want this add, but oh well, the area from 1 to 4. And then what I have is with 4, oh gosh. How do I, this isn't working as well as I wanted to. Oh, it's soon, okay. There we go. From 1 to 4 with 4 rectangles. Was that no, my question wasn't 1 to 4. Sorry. My question was 1 to 3. That's why the answer is different. The question that we had was from 1 to 3. So we get 8.75, and notice that's with triangles with the point that meets the curve on the left side of the triangle. If I click right, I get 12.75. If I increase, you can play around, see if I want the rectangles to intersect right at the center of the curve, like that, midpoint. You could use trapezoids. Whoa, that looks really good. But we just worked with left and right so far. What if you make like 10 rectangles? Then you see the right area is 11.48 and 9.88 for the left area. What if we go to 100 rectangles? 10.58, 10.74. Notice these are getting closer and closer to each other. Let's go to 200 rectangles. Wow, it looks like a really perfect, very close estimate. We see 2.62, 2.70s. We're still converging or closing in on the actual area, but clearly we're still not there yet. What if we go up to, let's see if we can go to 1,000. Whoa, maybe not. 1, 0, 0, 0. No, it doesn't like that. Let's try 500. No, maybe 200 is the most. Yeah, maybe so. Anyway, you see, or you get the idea. Feel free to play with this little applet. All right, that's it for the first part.